Okay, this is part 3, nonlinear binding. Another source of nonlinearity can be from binding. So, as you can see here, the binding is in the Michaelis-Menten form, and we have this relationship again between Kd, and which is our affinity constant, the concentration that's half of our where half of our binding sites are filled. So in most cases, Kd is much greater than concentration, and this falls out of the equation, and this would be linear binding, which is what happens in most cases. So as we increase our concentration, as concentration increases, we don't see any change in our fraction unbound. Our fraction unbound in plasma remains constant, so it's concentration independent in most cases. However, if this is no longer true and our concentration needs to be part of the equation, so it's concentration dependent, as we saturate those binding sites, as concentration increases, we're going to start to see an increase in the fraction that is unbound, an increase in our free fraction. I am going to also do nonlinear bioavailability, just so we don't have a million little videos here. So remember, bioavailability, we can have poorly soluble drugs where you will have a ceiling of what can be absorbed because it can't keep up with the amount of drug. So griseofulvin is non-linearly absorbed, so the Fa is non-linear, but it's simply because it can't get into solution when it gets into the higher concentrations. Any drug that is actively transported, then we know that's Michaelis-Menten, isn't it? So any drug that's actively transported from the gut to the portal system can also be concentration dependent, and amoxicillin is an example of that. Finally, we have high first pass drugs. So these are high E drugs where much of the drug is eliminated as it goes through the liver before it reaches the systemic circulation. So these drugs, remember, this is again the fraction that escapes first pass effect is dependent upon Q. If you remember this relationship, these two things are saturable. So nicardipine and verapamil can show concentration dependence in the therapeutic range because of saturable enzyme activity. So if you saturate those enzymes, what's going to happen to the fraction that escapes first pass effect? Well, if you saturate the enzymes, more of it's going to make it through without being metabolized, so the fraction that escapes metabolism is going to go up, isn't it? This is really due to intrinsic clearance nonlinearity, though. All right, I'm going to stop there.